Let's continue our introduction to circuit analysis by looking at two of the basic quantities you're going to be dealing with in this course. And those, of course, are the quantities of voltage and current. Voltage and current are words you've probably heard your entire life with respect to electricity. But many people confuse the meanings of the two and get them mixed up. They sometimes treat them interchangeably. But voltage and current have very specific definitions in circuit analysis. And let's go over those now and see how we're going to describe these things as we go through the course. So first, when we talk about voltage and current, we have to first consider the fact that voltage and current are really parts of the same phenomenon, and that is the concept of electric charge. So electric charge is, in fact, the basis for describing everything we're going to look at in circuit analysis and any type of electrical phenomenon at all. Now, electric charge is something you have certainly encountered before in your physics courses. Electric charge, for example, the idea of the charge on an electron or the charge on a proton. That's electric charge. So, what are the properties of charge? Well, first of all, charge has units. It has units of coulombs. Capital C. Second, charge is bipolar. And what do we mean by that? It means charge can be positive or negative, which we indicate by plus or minus for positive or negative. And charge also exists in discrete quantities. What is the smallest amount of electric charge you can have? It's the charge on an electron. And one electron, by definition, has a charge of 1.6022 times 10 to the minus 19 coulombs. So what we find is, when we talk about electric charge, all electrical effects that we can study in circuit analysis come about either due to charge in motion or the separation of charge. And as we're going to see, both voltage and current are described in terms of these ideas, of these concepts. Let's first look at the definition for current. By definition, current is the rate of charge flow. And we can mathematically describe that as I, where I is current, where current has units of amperes, or capital A, as we use as an abbreviation for amperes. I is equal to the change in charge with respect to the change in time, where delta Q divided by delta T, where Q is equal to charge in coulombs. Which we do with a capital C. And T, of course, is time in seconds. Now we can do this as delta quantities, or of course we can write this as a derivative, dq dt. And so therefore I is equal to dq dt, the change in charge with respect to the change in time. That's the definition of current. So using this equation, 1 amp must be equal to 1 coulomb per second, by definition. Now, here I've written this as a derivative, but if you think about it, obviously I can twist this around if I want to. I could also write this like so. If current is the derivative of charge, then charge must be equal to the integral of current. And you can use those definitions interchangeably. So that defines current. What about voltage? Voltage is electromotive force, excuse me. Voltage by definition is electromotive force. And you've hopefully heard that term before in your physics courses. And what do we mean by that? Well, electromotive force, a more detailed definition is that it is the energy per unit charge created by the separation of positive and negative charges. So you think about it. You learned in physics, positive and negative charges attract each other. So if you want to separate them and push them apart, that requires energy. And voltage, the electromotive force, is a way of describing this change in energy, change per unit charge, as you separate those charges, the energy expended. Mathematically, we can write this as V, where V is voltage in volts, capital V. It's equal to the change in energy with respect to the change in charge. So delta Q is the same thing we saw before, change in charge. Delta W, in this case, W is energy in joules. And once again, we can write this as a derivative and say this is equal to dW dQ. And so here's our mathematically precise definition for what voltage is. Once again, looking at the units, we can say that 1 volt must be equal to 1 joule per coulomb by definition. And again, as we saw, I can write this as a derivative, but again, I can flip this around and I can define energy in terms of the integral of voltage. So it's also true that energy must be equal to the integral of voltage with respect to Q, the charge. So W is equal to the integral of V dQ. So once again, these are interchangeable definitions depending upon whether you're taking derivatives or taking integrals. Now, voltage, current, clearly they have very different definitions. There is a nice little mental image people like to draw, which isn't completely accurate from a physical point of view, but it does help you to understand what is the difference between voltage and current, because lots of people tend to mix them up or use them interchangeably. And that is we call the pump analogy. So let's think about a pump that's pumping water through a circulating pipe. So here's our pump, a mechanical pump, and I've got a pipe, and as this pump runs, it circulates water through the pipe. So the pump is providing the force that pushes the water through the pipe. So this is a mental image we're really all very familiar with. And so as this pump runs, we're going to have water circulate through this pipe. And we can think of this water as, in effect, a current of water, right? Okay, it's the flow of water. And we're familiar with that, the idea of the current through a stream, the current through a river. It's the movement of water. Same thing here. So this flow of water is the current. The pump provides the force. Well, along those same lines, we can think of voltage and current the same way. Here we have a voltage source, and that voltage source is going to provide the force, the electromotive force, to push current through a conductor. And so just as the pump pushes water, the voltage source pushes electric charge. And so in this case, we're going to have electric charge moving through this conductor, through this electrical conductor, and circulating just as we saw water circulating here. And so in this case, this is an electric current. Which is just the flow of charge. So here we see that voltage and current are really two different things. Current is the result of voltage. In other words, we wouldn't have current if we didn't have the voltage creating that push, making that force. And so this is the consequence of that. And as we're going to see, mathematically, depending upon the component, there is a mathematical relationship between voltage and current that we could describe. Now, the last thing you need to know about voltage and current before we start moving on is to understand how they are quantified, how we describe them. Current is going to be described in two ways. It's described in terms of the quantity of current as well as the direction of the current as it moves through a conductor. And what do we mean by that? Well, for example, this is how I could describe current. Let's say I've got 2 points in a circuit, A and B, with a conductor connected between them, some path for electric current to flow. I'll describe that with a direction. I'll draw an arrow, and I'll describe it with a quantity. I'll say it has a quantity of 6 amperes, 6A. Now, here's something that isn't always obvious to everybody, but it's something you have to learn how to use as you learn about circuits. And that is that there is a mathematically equivalent way of writing what I just did here. To say that I've got 6 amps going from point A to point B is exactly equivalent to saying that I've got minus 6 amps going from B to A. So I can always write this as this by changing the sign on the quantity and then flipping the direction. These two are mathematically equivalent. And in fact, being able to use that equivalence turns out to be incredibly useful as you learn how to analyze circuits. Along the same lines, voltage, how do we describe that? Voltage we describe in terms of quantity and polarity. Let's look at an example to see how that works. So in this case, let's say I've got 2 points in a circuit, X and Y. I can measure or describe a voltage between those 2 points in the circuit, like so. First, I draw the polarity, positive to negative, between those 2 points. And then a quantity, 10 volts. So I've got 10 volts from X to Y, positive to negative polarity. Once again, however, we can use the same kind of mathematical flip that we did here with current. It is entirely equivalent for me to say, this is exactly like flipping the polarity and changing the sign and saying I've got 10 volts, or pardon me, I've got minus 10 volts from Y to X, or 10 volts from X to Y, positive to negative. And once again, flipping the polarity, changing the sign, flipping the direction, changing the sign, these are entirely equivalent. These are mathematically the same. And again, as you start to learn how to work these problems, this will become second nature to you. This is something you will have to learn how to do in order to how to understand your answers and how to analyze the circuits you're going to be working on. Okay, so that covers our basic definitions of voltage and current. Next time we will look at the definition of a circuit element and start looking at how we can start putting these things together and describing these quantities mathematically.